Okay, this is the beginning of chapter 14. Chapter 14 has to do with chemical equilibrium. Chapter 14, 16, and 17 are all very closely related, dealing with equilibriums. This is a generic chapter that covers all equilibriums, whereas 16 and 17 are specific equilibriums. You notice I skipped 15. 15 kind of takes a break from this. We talk about acids and bases, information you need to know before you go to 16 equilibrium. So equilibrium is a reaction that doesn't go to completion. Okay, so basically it's the body has lots of equilibriums, but for this context, basically think about the blood and the O2 level. Okay, very seldom does the blood have 100% oxygen or 100% carbon dioxide. It has a mixture of those two things, and so that's an equilibrium. So an equilibrium is characterized by the final mixture, or the products, or what's in the flask, I should say, after it reaches equilibrium, contains both products and reactants. Up until now, we've been talking about reactions going to completion, which means they only contain products. They may contain one reactant, but not both reactants. So since the products and reactants are being formed at the same rate, okay, this is called a dynamic equilibrium, which basically means that the reaction is going forth and back. We symbolize equilibrium by using a double arrow like this. This is showing the fact that it's going forward and it's going back. So initially, I have a mixture of A and B's. Okay, so I have 28 A's and 15 B's. As it goes forward, but before it reaches equilibrium, I go to 20 A's, 11 B's, 2 C's, and 2 D's. So I've formed some C's and D's. Okay. It continues to decrease in A's and B's. Well, B actually increased briefly there. Increase in C's and D's. And then at equilibrium, when the mixture is done, and this means it will be constant at this point, I have 11 A's, 10 B's, 8 C's, and 8 D's. So all of these components are inside this reaction flask at the same time. And that's when equilibrium is. So this is showing a figure out of the textbook that this is the reaction of 3 hydrogens plus carbon monoxide goes to form methane plus water. So you see that the hydrogen and the carbon monoxide are decreasing in concentrations because they're reactants. And the methane, the CH4, and the water are increasing because initially it starts at 0, but as these two things go to react, it forms these two things. But all 3 lines level out, so there's not a change in concentration over time. And when that happens, that's called to be the equilibrium rate, equilibrium amount, or equilibrium mixture. So the forward rate versus the reverse rate, when those two basically line up and come to be equal, then that is when an equilibrium is reached. So we're going to start out, and this is something that we're going to use in those 3 chapters, 14, 16, and 18, or 17. We're going to start with what they call the ICE table. So this is maybe something that you've heard referred to before. Our book tends to deal with starting amounts, changed amounts, and equilibrium amounts. So basically the only one that's different is the starting, and we say initial with the I. Okay? So you're typically given starting materials. So you're given an amount of all the reactants. And typically one of the products, although it doesn't have to be a product, we're going to do a problem in which they actually give you another of the reactants at equilibrium. So you write the balanced equation, which is usually given for you. You create an ICE table. You find the change for one that you have both the initial and the equilibrium amount for, and apply that change for all of the other reactants. So let's do an example of that. So in this problem, we have 2 sulfur dioxides plus 1 oxygen goes to form 2 sulfur trioxides. And it tells me when I have 0.6 moles of sulfur dioxide and 0.6 moles of oxygen placed in a 1-liter container and allowed to come to equilibrium, the equilibrium moles of SO3 is 0.250. So what's the equilibrium concentration of SO2? So if I go back, the first step is to write the balanced reaction. Well, it's given to you, but I'm going to write it down below here anyway, as I can find my pen. Wrong pen. It doesn't work with a normal pen. So I have 2 SO2s plus O2 in equilibrium to 2 SO3s. Okay, and I'm going to make an ICE table, so I, C, and E. And then I plug in my I amounts, which it tells me I have 0.60600 moles. This is a 6. And 0.600 moles. And unless it tells me, I'm going to assume that my initial amount of my product is 0. We're going to come into problems where that's not the case. Now, change. A reactant, just like this part we did like kinetics, is negative times the coefficient. And a product is positive times the coefficient. I dropped a IC in the first one, but that's okay. So this being a reactant, it's negative, and then the coefficient is 2, and then I put X. So there has to be an X for each one of these. This one is still a reactant, so it's negative. The coefficient there is assumed to be 1, so we don't write anything, X. And this one being a product is going to be positive, and so it's 2 and then X. And then it says the equilibrium. So this is going to tell you that the difference is that these are placed, that means initial. And this one says equilibrium. Okay, so the equilibrium amount of SO3 is 0.250 moles. Now, which one of these species, SO2, O2, or SO3, do I have both the I and the E for? And it's the SO3. So the reaction is that I really don't want to do that there, sorry. I plus or minus C is equal to E. So it's 0 plus 2x, because this is positive, is equal to 0.250. So basically it simplifies down to 2x is 0.250. So x is 0.250 divided by 2, which gives me 0.125. And that's x. Okay? So now I'm going to come over here and I'm going to plug in this x in this equation. So it's still I plus or minus C is equal to E. So it's going to be 0.6 minus 2 times the 0.125. I don't know what it's equal to yet. So it's 0.600 minus 0.250. And when I do that, I get 0.350. And units is moles. Okay. So, oops, this answer goes there. Now I'll change colors. And for this one, it's 0.600 minus x. Okay, so 0.600 minus the 0.125. And when I do that math, I get 0.475 moles. So that goes there. And so my overall answer for this problem is right here on my sheet. Okay? And I will make a second video with a second example of this process.